tomorrow. And that test is going to cover metallic bonds. Well, you'll have to make it up. You'll have to make some sort of arrangement. Who's me? Who? Simpson? Okay, Ethan, you'll have to make it up. You'll have to make some arrangement, okay? All right. Metallic bond is section. It's up to you. Yeah, I'm just telling y'all what the deal is. Yeah, we're taking a short test tomorrow. It'll be about 25 questions, and it's going to cover section 3, metallic bonds. You know, the electron C, all the properties it gives, right? What do we use as the measure of strength of a metallic bond? It's all of them. Yeah, all of them are kilojoules per mole. Enthalpy. Yeah, good.
Oh, okay.
Remember, you got bond energy. What does that measure? Covalent, metallic, or ionic? Covalent. You got enthalpy of vaporization, metallic, and then lattice energy is ionic. Okay, let me give a list of what we're doing, and then we'll go through and we'll review. Ionic bond in section 6.4. Then there is a couple of things I want to add to this. We'll do in just a moment. And then intermolecular forces. And this is the back end of section 5. From page 203. 207. We're going over that today. We're going to keep it very basic. Ready? Okay. For a short period of time.
You was?
Yeah, for a very short period of time.
Like a month or a year?
A year. I didn't like it. I was a majorette and I like that better. It's less drama. Let's do this. Since we've covered ionic, the only other thing that I want to talk to you guys about ionic is how its strength compares to molecules, covalent. So we'll do that at the end. There's a thing about molecules. Remember when we melted the sugar, and then we burnt the sugar, then we melted the salt, right? Okay, let's focus on the sugar. It takes, what do you remember about it? Yeah, let's pause this video for just a moment. Okay. I'm just making a simple model because I don't want to try to draw that Lewis structure. Sugar molecules, right? Okay. What's inside here? Covalent.
So does covalent only work with molecules?
Yeah.
So how can you tell if it's molecule?
Remember, if it's all non-metals,
Oh, okay.
remember? If it's ionic, it's got a metal and a non-metal. If it's metallic, it's all metal. Okay? All right. What are these green dots? Intermolecular forces. I'm going to call it IMF for short. Okay. When we first heated up the sugar, it turned to a liquid. What did we break?
intermolecular forces.
Yeah, when we melted, we overcame that. And we had liquid sugar molecules that were free to move around. That's what causes something to be a liquid. Solid, the particles are stuck in one spot. And they can't move from one spot to the other. In a liquid, they can move, right? All right, so when we melted the sugar, we broke intermolecular forces, but the molecules stayed intact. Then when we burnt the sugar, what did we do? We broke the covalent bond, and we ended up with black carbon and water. And that's what the vapor was you saw coming up the test tube. Now, what does that tell you about the strength of intermolecular forces compared to covalent bonds? Which one's weaker? Good. That's what I want you to see.
Why is that?
Because they're not a covalent bond. I'm going to put a few notes up here. Okay, intermolecular forces are weak. Well, I don't want to say weak. I don't want to say that. They are attractive forces. That hold together molecules. Hey, look at the periodic table, please. Do all elements form chemical bonds?
No.
No. Who doesn't?
Hydrogen. No.
Yeah.
Helium. I don't know.
Noble gases. What semester of chemistry are you in?
Second. I didn't think about that one.
So, since there's no chemical bonds between noble gas atoms, what holds them together? Intermolecular forces. So intermolecular forces hold together molecules and noble gas atoms. They are not chemical bonds. When I say they, I'm talking about intermolecular forces. Are not chemical bonds. They are not chemical bonds. They are weaker than chemical bonds. So it's like we have a hierarchy of forces of attraction. We'll get to that in a minute. At the bottom, the weakest are intermolecular forces. There are three types of intermolecular forces. Pre-AP is getting into the nuts and bolts of how these intermolecular forces work, but you guys will not. We're out of time. We got to move on. So we're just going to look at the basic of it, how one's different from the other. So that means note-taking. Okay. Number one, London dispersion forces. They are also called van der Waals forces. Skip a space, because I'm going to add some stuff to this in a minute. So let's skip 2 lines after London forces. Number 2, dipole forces. Skip 2 lines. Number 3, I hate the name of this thing. Absolutely hate the name of it, and you'll see why. hydrogen bonds because it's not a chemical bond. It's not a chemical bond. It's an intermolecular force. They named it hydrogen bond, and every chemistry teacher hates it.
Because
it
hydrogen
confuses-
bond.
Well, I'll show you what it is, but it confuses people. When you're first learning this stuff, it's really confusing. It's got the word bond in it.
Things get any.
Okay. London dispersion forces. They are IMFs. Between all molecules and noble gases. But why are they significant? They are, I'm sorry, they are the only, sorry, yeah, we're playing beat the clock, I'm sorry. It's January, we have got to start writing names and formulas of compounds and balancing equations and get into chemical reactions. I mean, we could spend a month on this stuff, but we just don't have a month. Okay, they are the only IMFs that hold together. They are between non-polar molecules and noble gases. What I mean by that is everything, all molecules have London forces. But polar molecules have this plus other stuff that's stronger. These things are the weakest. London is the weakest intermolecular force. Now, I could get more technical with this, but I'm not going to. But if you are curious, you know, you can Google it or you can read about it. I wish I had more time, but we don't. But basically, these are what we call induced. They're caused by when atoms or molecules get near each other, the nucleus is going to attract, but the electrons are going to push other electrons away. Blah, blah, blah. Moving on. Dipole-dipole forces. They are intermolecular forces between polar molecules. Polar, remember polar covalent, right? Unequal sharing of electrons. These are the forces that hold them together. Yeah, they have London forces too, but the dipole-dipole are stronger, so it kind of makes the London forces insignificant. Hydrogen bonds. Especially strong dipole-dipole. hydrogen bonds are dipole-dipole forces, but when you've got a molecule where hydrogen is covalently bonded to either nitrogen or oxygen or fluorine, look where they are on the periodic table. Those are the most electronegative atoms. Nitrogen, oxygen, and fluorine spelled not. They are electron hogs. So when hydrogen way over there bonds to one of those guys, there is a very unfair tug of war happening. And Na is going to hog those electrons. And that creates a really, really strong difference in charge, partial charge. Water has this. Hang on. You can do this at home. But I want to demonstrate just how strong hydrogen bonds are. At home, take you on your water faucet, get you a really thin stream of water. It needs to be thin because, you know, water's heavy and you've got to overcome gravity here. I know, it's 40 some odd years old. Take your drinking straw and you can rub it with your hair. But it doesn't work as well if you have a lot of styling products on your hair, so I'm going to use that because my hair is stylish. Okay, we're going to rub in one direction. We're going to get static electricity, a bunch of electrons on this rod, right? Don't touch anything with it, because what happens? The electrons will go to the ground, right? So don't touch anything. And then bring the straw near the water.
Oh, that's great.
That is cool.
So try this at home. Impress your family, impress your friends.
Don't make home all. I call it myself.
Now, if
Do
you
that
touch
water
the
on the
water,
side.
electrons are going to make its way to the
It's
ground.
bunch. You got water squirting on the side.
No, because,
Won't work or.
no, I mean, it's better to have it free flow.
Must be Jenna.
Pretty cool, huh? Okay, y'all try it for you leave. Okay. Do it at home. See, now what's going on here? What's happening is you got that thin stream of water, right? Okay, water is a whole bunch of that, right? You got null right there. You got hydrogen bonded to oxygen. Big, you know, you got hydrogen bonded to hydrogen bonded to oxygen here. You got big difference in partial positive and negative charge. A really polar molecule. So that creates a really strong attraction from here to here, from the partial positive to partial negative on another. So this is a hydrogen bond, which we just call H bond. And since it is so strong, you bring that rod, your straw has all these electrons on it. You bring it near the water and tell me, if this is partial positive and the oxygen is partial negative, which end of the water molecule is attracted to these electrons? The positive, the hydrogen end. So when you bring the straw, I'm going to turn it off for a second, it's leaking everywhere. When you bring the straw near the stream of water, it's like all the water molecules, they move so that the hydrogen ends are here, and they're attracted to the hydrogen ends are trying to get near that straw. And you move the straw and it pulls the water. That's how strong these hydrogen bonds are. Okay? That's all I'm asking you about intermolecular forces. Last thing. say, which was easier to melt, sugar or salt?
Sugar.
So what does that tell you? Which is stronger, the bonds in sugar or the bonds in salt? Good. We're not going to put metallic in this. That is why it took less energy to melt the sugar. These are weak. They're not even a chemical bond. But then we're able to burn sugar with a lighter. Not a lot of energy. That means they're not quite that strong. But it took that big old meeker burner to melt the salt, which means it takes a lot of energy. They're really strong. Y'all got that? So we use melting point. You'll do this in your lab. We can use melting point as a measure of how strong the bonds are. So ionic substances have higher melting points and boiling points because the bonds are stronger. Now, one more thing about ionic. These are a whole bunch of positive and negative ions, right? Okay, ionic will conduct electricity if molten. What does that mean? Yeah, or dissolved. Because when you dissolve, you're breaking ions. You're breaking the lattice apart into ions. That's it. That's test tomorrow. All right, guys. If you got any questions, I will be here at 7:30 for tutoring.